Good morning. Good afternoon. So let us start. Okay. So suggest everyone to join quickly. Okay. Today's class we'll be looking at Miller's theorem, okay, and solve a couple of problems. All right. So first thing, let us slightly recap. Okay. Okay. So in the last class we discussed how to find out the 3 dB frequency, cutoff frequency, okay, of the high frequency response of a amplifier, okay, a MOSFET amplifier. Right? We derived omega h as 1 divided by square root of 1 by omega p1 square plus 1 by omega p2 square plus so on, right? Plus so on. Minus 2 into 1 by omega z1 square plus 1 by omega z2 square plus so on. Okay. So this was the general omega h. So here omega h is the 3 dB frequency. 3 dB frequency. Omega pn. Okay, those are your poles. And omega pz. Omega zn. Okay, those are your zeros. Okay, these are your zeros. Right. So this is the general expression for omega h. Right. So in the last class we also saw. Right, we saw a problem where we calculated fh as 1 by 2 pi omega h. It is same as 1 by 2 pi into. We solved a problem for an amplifier. We calculated two total time constants. Right, one is tau gs and one is tau gd. Okay. Now the thing I want to point out here is fh depends, should be as high as possible. As high as possible. Okay, it should be as high as possible. So to make fh higher, okay, fh actually depends on tau gs in the case of that example. Okay, it depends on tau gs and tau gd. And if I remember correctly, tau gs is actually we found the value to be 80.8 nanoseconds, and tau gd to be somewhere around 1160 nanoseconds. Right. So if I look at this equation, if I substitute these values in fh, I got the fh value as somewhere around 12.8, 128.3 kilohertz. Right. So here fh depends on tau gd a lot. Okay, meaning tau gd actually is dominant here. That is what I mean. Okay, tau gd is dominant here. So what I do is, if I try and reduce tau gd, okay, then my fh will actually increase. So that is a good thing. So to get a higher fh, okay, tau gd has to reduce. Okay, tau gd has to reduce. But tau gd is actually r times gd into cgd, right? And rgd depends on depends on R prime and RL prime. Okay. See, this whatever analysis I'm doing here, it is pertaining to the previous example which I solved in the last class. Okay. So by looking at that example, I'm drawing some inferences. Okay. So here tau GD is RGD into CGD. Say tau is equal to R and C, R into C. It is a time constant, right? And RGD depends on R prime and RL prime. Remember, in RGD, we have derived it. In the problem, we have derived some expression in terms of R prime and RL prime, right? So to get a higher FH, tau GD should reduce. So the scope for me to reduce is I have to choose a MOSFET with lower CGD, okay, or I have to reduce RGD, okay, to get higher, a higher FH, okay. So I either have to choose a MOSFET which has a lower amount of CGD, okay, capacitance between gate and drain is less, or I have to reduce RGD, okay. But here RGD depends on two values. RGD is actually proportional to R prime and RGD is proportional to RL prime. Okay, on a side note, R prime is actually R in parallel R signal, and RL prime is actually the three resistance circuit drain RD parallel RD, which is your drain source resistance, parallel RL load resistance. Okay, so say by chance if R prime is constant or fixed. Okay, if it is constant or fixed, I have to reduce RL prime. Okay, I have to reduce RL prime. I have to reduce this. I have to reduce RL prime. Okay, so RL prime by reducing RL. Okay, by reducing RL prime can be reduced. Why I'm targeting RL is because see, small RD, which is your drain source resistance, is not in your hands, and capital RD is set by the biasing scheme, which biasing scheme you use, right? So the only thing which I can control is RL, the load resistance. But if you remember correctly, right, your gain, okay, gain is actually V0 by Vc. So it is minus Gm into RL prime into Rn by Rn plus R signal. Okay, this is gain, overall gain. Okay, overall gain of the circuit. Right. So this part is actually AV. Okay, this is due to the input voltage divider configuration between Rn and Rc. Right. So here, if RL is reduced, okay, RL is reduced, then overall gain is also reduced, right? But see, that is the trade-off here. Okay, it is actually called gain and bandwidth trade-off. Gain and bandwidth trade-off. Okay, gain and bandwidth trade-off. If I want to improve my bandwidth, I have to reduce my gain. If I want to improve my gain, if I want to improve my gain, I have to reduce my bandwidth. So this is actually called a bandwidth and gain trade-off. So if FH increases, if I want to increase FH, I have to reduce RL. If I reduce RL, my overall gain will actually reduce. So this is the relation. Okay. I hope this is clear. So this is the trade-off between gain and bandwidth. To improve gain, I have to reduce bandwidth. To improve bandwidth, I have to reduce gain. Okay. All right. Next topic. Any queries till now? Right. This is actually a continuation of the problem which we solved in the last session. All right. I've not made any inferences in the last class, but keeping that in mind, I have continued it. Okay. Always remember the last point. In order to increase your bandwidth, you have to reduce your gain. In order to increase your gain, you have to reduce your bandwidth. So again, this depends upon which application you are using, right? Okay. Then in that case, let us move on to Miller's theorem. I believe you have already learned Miller's in AEC. Miller's theorem. Okay. So what Miller's theorem states is that if I have a impedance which connects both input and output, okay, I can actually replace that input impedance. I can see if any impedance connects input and output. Okay, then Miller's theorem says that impedance can be replaced by two sets of impedances. Okay, and although the condition here is that the same amount of current should flow. Right. So Miller's theorem is especially useful for separating out input and output sections of the circuit. Right? So if I roughly draw it, this is say the impedance Z which connects input and output. Okay, so this is V1. So this is V2. Okay, the current flowing with this is I. Current flowing with this is I. Okay, here V2 is V1. K times V1. Okay, so K here is a gain magnitude. It's actually gain, not gain magnitude, it's gain. It is gain. Right. So this circuit can be represented like this also. Okay. I can replace Z with say some impedance Z1 at the input side. Okay. This I will call it as V1. Okay. The current flowing I will call it as I1. It is same as I. Right. And at the output side, okay, I get an impedance called Z2. Right. And here I have V2. I have V2. V2 again, V2 is K times V1. Okay. And the current which is flowing here, if I call it as I2, that should be same as I. Okay. All right. So this is what basically Miller's theorem is. Okay. Now the proof of this. Okay. Proof. Okay. Proof is actually very simple. If I take this circuit, okay, select this. So select this circuit. Okay. Now in this, what I do is pay attention. I want to find Z1 now. Okay. Before I mention that, here I write Z1 as Z divided by 1 minus K and Z2 as K Z divided by 1 minus 1 by K. Okay, just to know, right? We'll prove this now. All right. So here to find Z1, what I do is I short my input. Okay. I short my output. This is to find Z1. Okay. So it will come like this. Okay. This is Z. And this is like this. Okay. This I will call it as current I1. Okay. This is V1. Okay, that is it. All right. So from this short output side. Okay, short outputs. So what I do is from this circuit, okay, if I apply KVL, okay, KVL, then I get V this is plus and this is minus, right? So we should plus so V1 minus I1 Z equals to 0. V1 minus I1 Z equals to 0. So I1 is I1 is V1 by Z. Okay, but the condition is I1 has to be same as I. Okay, so from this expression, from this, I can write I as V1 minus V2 divided by Z. Okay, so remember on the right side, on the left side, whatever I've written is for the shorted output side. I've taken KVL, from that I've written I1 is equal to V1 by Z. On your left side, this part. Okay, I've written I is equal to V1 minus V2 by Z. This is obvious. It's simple only. Okay. Right. Now, Miller's theorem states that for Miller's theorem to be actually valid, for Miller's theorem to be valid, okay, I1 has to be same as I. Okay, I1 has to be same as I. Then in that case, V1 small correction. This is actually Z. Okay. Although this is Z, the impedance which I'm seeing is Z1. Right. So V1 by Z1 is equal to V1 minus V2 by Z. Okay. So V2 is K times V1. So V1 minus K times V1 by Z. Right. Solve it. You'll get Z1 equals to Z divided by 1 minus K. Right. So first equation. This is my first equation. Right. So at the input side, I can replace Z with Z1, which has a value Z by 1 minus K. All right. Now the same thing I'll do at the output side. Okay. So I'll copy this once again. Okay. Now I have found Z1. I have to find Z2 now. Copy this. Now to find Z2. Okay. I have to short the input side. So input side, if I drop, it will come like this. This is Z. This is this. This is V2, which is K times V1. This is current I2. Okay. And this is plus minus. And the impedance which I see in this direction, that is Z. Right. So if I apply KVL, okay, if I apply KVL like this, right, if I apply KVL, then I will get minus I2 Z2 minus V2. Okay. Okay. Equals to 0. From this, I can write I2 as minus V2 by Z. Okay. Minus V2 by Z. So this is with respect to the KVL. Right. Now from this, okay, if I write the same thing, no, if I write I, expression for I is V1 minus V2 by Z. Okay, same thing. Right. So from this, Again, for Miller theorem to be valid, okay, I2 should be same as I2. Okay, so minus V2 by Z2 should be V1 minus V2 divided by Z, and V1 minus V2. V2 is K times V1 divided by Z. So solve this, and also here V2 is minus K times V1 by Z2 is equal to V1 into 1 minus K divided by Z. V1 will get cancelled, right? Then Z2 is actually Z divided by 1 minus. Okay, this is the second equation, right? So from this we have just proved Miller's theorem. This is what Miller's theorem is. Right? The reason we need Miller's theorem is to actually separate my inputs and outputs. See, under high frequency analysis of MOSFET, right, you have a capacitance which connects between gate and drain, right? So that will show up in the small signal model, right? So I don't want it to complicate my analysis. So what I do is that CGD which I have, okay, that I will write it in this form. Okay, I will divide it into C1, Z1. I will divide it into Z2. Replace that CGD with Z1 and Z2. Okay, to perform my analysis. Now it is easier, right? So I can associate Z1 as the input side and Z2 as the output side of the circuit. Right? So your inputs and outputs will be clearly separate. Okay. But if I have a capacitance, right? If I have a capacitance instead of an impedance, right? Then in that case, what would be its Z1 and Z2? Right? That we see now. So I have V. So I have now V1. Okay, V1 which is like this. This is a capacitance here. So since we are dealing with the capacitance, right, and not some resistance, so I have to worry about capacitance. So if I call this capacitance as C, this as V2. Right, this is current, say I, this is also current I. Right. So this equivalent model would be like this. I have a capacitance here like this. I have another capacitance like this. This is V2. This is V1. Okay. So I have to find the values of these with respect to C. Right. This I will call it as I. This is also I. Right. So if I call this as Z1, this is Z. Right. I have to find the values, not values. I have to find Z1 and Z2 in terms of capacitance C. So Z1 here is Z, okay, divided by 1 minus K, which we already proved earlier, right? Remember, V2 is K times V1. K times V1. Right, so Z I have to write it as this, 1 by SC, correct, divided by 1 minus K. So in this, I will write it as 1 by S into C into 1 minus K. Right. So this Z1 which I have, that I write it as 1 by S C1 is equal to 1 by S C into 1 minus K. Okay, so from this I can write C1 as C into 1 minus K. So the capacitance which you are getting at the input side, this capacitance, it will be multiplied by a factor of 1 minus K. Okay, so it will actually get multiplied by a factor of 1 minus C into 1 minus K. Okay, similarly we'll find out for Z2 also. So for Z2, I know Z2 as 1 by SC2. Okay, it is 1 by SC, which is Z divided by 1 minus 1 by K. Okay, so from this I can write 1 by SC2 as 1 by SC into C into 1 minus 1 by K. Alright, therefore C2 here is C into 1 minus 1 by K. Okay, so this is what C2 is. Alright, so in that case, this will actually be C into 1 minus 1 by K. Okay, so see, remember this is the gate part. This is actually gate, and this is actually drain, right? And this capacitance which you have, that will be CGD, right? So this will actually come very handy when we are doing a high frequency analysis for common source, common drain, and common. Okay. So try and understand this. Okay. Always remember, if you have a capacitance between the input side and the output side, at the input side, you replace that capacitance with the equivalent capacitance C1 multiplied by a factor of 1 minus K. And at the output side, you have an equivalent resistance, another equivalent capacitance is multiplied by a factor of 1 minus 1 by K. Right? So that is what I wanted to show you. Right? Now, look at a small problem. Right. So what we do is in this. Yeah. Any queries? Do you have any query? All right. So in the problem, you have an op-amp, okay, which provides a gain of 1000 minus 100 inverting amplifier. Right? Here it is simple. Okay, so I'll just draw the figure. This is B signal. This is R signal, which is actually 100. 10 kilo. This goes to an amplifier, okay, which provides a voltage gain of minus 100 volts per volt. Okay. This is going to be okay. The voltage seen between these two points. Okay. VI. Okay, and you have a feedback resistance like this. Z. Okay. Feedback resistance Z. Right. So what is asked is find the Miller capacitance, Miller equivalent circuit. Miller equivalent circuit. Okay. Then okay, first bit is when Z is equal to 1 mega ohms. And second one when Z is a capacitance, which is 1 picofarad. Okay, and for both these instances, find V naught by V signal. Okay, so both these instances find V naught by D sigma. Alright. So anyway, we have 5 minutes. I'll exit this meet. Okay, and kindly join back. Okay, I'll